Yeah, all of you just look this side. So, if you don't receive a message from me and you feel like I should have been in the class, then you should write back to me, because we are having some problem with Canvas and EEE plus being replaced. So, you might miss a message from me. Half of the class gets it, half of the class doesn't get it. So, go through announcements, and now it's your responsibility that before the discussion or before the session, like on Thursday night and Friday nights, just go and watch your announcements. So, today I will be doing a recap. First 30 minutes will be a very fast recap from week 1 to week 3, and then the last 15 minutes will be a sample example. I would suggest all of you put away your iPads and scratch papers away and listen to what's happening. Then I'll provide you with some cues. You can go back home, rewatch the lecture if you want to. Otherwise, you can write your own notes later on. But it is very important that you see all of this today in one fresh perspective or together at once, because next week, starting next week, you will be entering into equations of motion and Euler angles, which is very different from what you have been doing until now. So, that is a kind of a new module to this course. So, this week was the last module, last week for the first module of the course. So, before we jump to that, so I hope everyone is familiar with the fact that these are the axes. So, this is x body, this is x body, this is x body. Small b, cap b. I should be using cap b. Okay, this is positive y body, this is positive y body, and this is positive y body. Z is inside, so I will put it with a cross. This is z body, positive z body, positive z body. Okay. So, first of all, what we were dealing with, the velocities that you have in each of the sides. So, the velocity in this direction is given as u, the velocity in this direction is given as v, and the velocity in this direction is given as tub, small tub. Okay. And what are the forces? Again, recall, it's very simple. We denote the force in x direction as cap x, in the y direction as cap y, and and cap z in the z direction. So, this is all good. Now, the problem happens with conventions of signs in pitching moments, rolling moments, and yawing moments. Okay. So, remember that your positive y axis is like, if you are looking on the aircraft from its left, your positive y axis runs into the paper. So, you point your thumb towards the positive y axis and curl your fingers. So, this is the positive pitching moment, which is denoted by cap m, and its coefficient is denoted by c sub m. Okay. Then you got introduced to two more terms, which was rolling moment and yawing moment. So, now you have this x, right. So, you point towards x, and if the aircraft rolls this way, okay, and similarly if you have z and your fingers curl this way, then this is the best diagram to make. Did you get? So, the main takeaway from this, making these three sketches, is, can you guess why I had to make three sketches? Because when you are doing a giant problem which involves all of these things, yawing moment, pitching moment, and rolling moment, so you can see that clearly this figure is much better to solve a question when you want to do it with rolling moment. This figure is much better when you want to do it with pitching moment, and this figure is much better when you want to do it with yawing moment. you are definitely going to make mistakes in yawing moment and rolling moment signs in this picture. Okay. So, remember the first trick is like you have to know which figure to draw in the first place. Okay. Okay, so now we will keep this as it is and let us keep moving forward. So, the labeling and geometry, now we are good on that. So, recall that first of all you were the first thing that we were taught were like longitudinal stability. The major important question is like what is the primary requirement for stability in pitching axis, or in what should be the first thing that you learned, that what makes an aircraft stable in pitch?
Cm alpha is negative.
Yes. So, the first thing that you learned was that Cm alpha is negative, and this is for the entire aircraft. And remember that wing has a destabilizing contribution and tail is used to stabilize it. Okay. Now, the second question is, now we are going to move forward to operating conditions such as trim. So, what do you think Cm alpha, like what should be the value of Cm naught? Remember? Yes, Cm naught should be greater than 0. Best way to understand it is graphically, that let us say we have two candidates, this is candidate 1 and this is candidate 2, and we are plotting Cm alpha versus, oh sorry, not Cm alpha, Cm versus alpha, and both have Cm alpha negative, but one of them has Cm naught positive and one of them has Cm naught negative. Now, I told you that looking along this axis you will not get the answer, you have to look along this axis. So, here the operating point, what is operating point at which Cm is 0, here the alpha operating is greater than 0 and here alpha operating is less than 0, and we know that for positively cambered airfoils we need positive angle of attack. So, we would want a positive alpha operation, and that is why we prefer Cm naught greater than 0. Okay. So, this is fact 1, this is fact 2 of module 1. Okay. Now, moving on, the next thing that we discussed was CG limits and trim. Stop me anywhere if you are not able to follow along with the speed that I am going. You should be able, this is a recap now. Okay. So, what is the first thing that we realized? That we defined something called the static margin, which is given as x neutral point by C bar minus x CG by C bar. Why? Why should static margin be positive? What happens when static margin is negative, is 0? What happens when it's 0, when it's greater than 0 and when it's less than 0? What is the definition of neutral point?
Pitching moment, when sum of moments is 0.
Sum of pitching moments is going to be 0, right? So, if your CG is aft of the neutral point, then what's going to happen? Huh? It will be, the static margin will be positive. Aft means after.
It will get a contradiction with like the condition of
Yeah.
stability condition.
This is CG location 1, this is CG location 2, and this is like let us say CG location 3. Okay. So, remember that aft, so this is aft location, this is fore location or forward location, and this is at the neutral point. So, this is unstable. Okay. Why? Because we have another definition which tells me that this is equals to negative Cm, oh no, not this ink, where is my black marker? Now I'll have to edit this out. Does anyone see my black marker?
In your hand?
Why are you not seeing that? Minus Cm alpha by Cl alpha, which is negative dCm by dCl. Recall this, that this is the entire expression actually, which should always be there in your head. That static margin, I mean the math and the symbol should not be there in your head, but what should be there in your head, that static margin is related to neutral point, Cm alpha and Cl alpha somehow. I do not know how, but I will recall it in the exam hall. I mean, if you know the basics, you can come to this equation within 5 minutes, but you need to know that it was neutral point Cg, Cm alpha and Cl alpha, right. Now, we know that Cl alpha is positive, and we know that for stability, inherent stability, we would want Cm alpha to be negative, which means that positive, negative divided by positive, negative times negative positive. So, for inherent positive, inherent stability, we want static margin to be positive, which means that neutral point should be after the Cg, aft of the Cg. So, here neutral point is 4 of the Cg. So, this is unstable. Then you have here Cg is 4 of the neutral point. So, this is stable. And anybody wants to guess what is this position called? It is called marginally stable. So, do you understand the concepts between something being stable, unstable and marginally stable? If not, this should clarify things. So, let us say that this is your aircraft again and this was your neutral point. Okay. Let us say you had a CG that was ahead of it, right. What happens? A gust hits, it suddenly increases the angle of attack, but it is inherently stable. So, it comes back, right. So, what happens if I look at, let us say, if I were to conduct an experiment looking at the angle of attack of the aircraft with respect to time, and let us say at t equals to 0 suddenly a gust hits. So, I was flying at 5 degrees and suddenly I was shot up to 15 degrees, but then my aircraft was stable. So, very slowly I came back to 5 again. Okay. So, whatever disturbance was given to you, you were able to mitigate it and come back to the operating condition. What if your CG was behind this? So, it is unstable, which means that you are going to get a sudden, so this was your sudden increase in angle of attack, but then this just keeps on growing, it is not able to come back, ultimately you will hit stall. Got it? I mean, there is no line after certain time because you have lost lift, dead. Okay? And then you have marginal stability. Marginal stability says that if you disturb it, give it 10 degrees, it is not going to react at all. It is going to keep flying at 10 degrees. There is no tendency to go away or come back. So, it is like the same problem, like a ball on a curved surface, unstable, a ball in a bowl, stable, a ball on a flat surface, marginally stable. Do you get that? Okay. So, and then the last topic in this sub part, you can say, was CG limit, to be exact. Now, pay very careful attention, pay attention, okay, because a lot of facts come into this thing. So, now you all know that the most forward CG position occurs during landing, and it is the most crucial phase. Why? There are a lot of factors at play, and they are all of them, I mean, depends on case by case basis, but in general aviation or passenger aircrafts, especially in bigger aircrafts, they do carry weight. You cannot neglect them when you are designing an aircraft. Okay. So, landing speed determines like how big, like the softer you want to land, the bigger your elevator trim tab should be. Okay. So, what is happening at landing? So, first of all, actually I would want to give it more attention. Actually this is better. Let me bring this down. Okay. So, all of you know that in passenger aircrafts, like the inside of the wing looks something like so. These are some electronics and flaps, these are some reinforcement, these are I-beams, and this is hollow. Okay. And can you guess what's there in this hollow? Fuel tanks. Okay. So, the fuel is here. Now, see what happens, like at landing, what's going to happen? First of all, you need to slow down, right? You don't want to land hot. And second, if you want to slow down, which means you want to like land at the slowest speed possible, which means you have to balance your weight with the slowest speed possible. So, in lift, if we have the dynamic head times area times CL times alpha, and if you need to drop the dynamic head, what is the only thing that you can change?
CL alpha.
CL alpha, right? Actually, okay. So, the only thing that you can change is, so you will have to keep alpha at alpha max. So, alpha max occurs at landing. The first question that you should be able to answer after leaving this discussion, that why alpha max should be positive is maximum at landing. Okay. Now, look what's happening. So, you all know that if I look from the top, right, then the wing looks something like this, right, swept back, and you know that the fuel is filled up here. What's going to happen over the entire period of the flight? The fuel is not a negligible part of your aircraft, let me tell you. It weighs more than all of us sometimes, okay, like the passengers included. So, what will happen? Let's say the fuel was here and the CG of the wing was here and the CG of the entire aircraft was somewhere here. The fuel got emptied, and obviously because the fuel is no more here, this CG would be here, and now the aircraft CG would move forward. Okay. So, what's happening?
Moments would decrease.
No, actually I didn't ask the right question. Let me give you an even better thing. So, what's happening with the static margin? It's increasing, right? Which means the aircraft is becoming more stable. But here is the problem. As a pilot, do you want the aircraft to stabilize and come back, or do you want to keep flying like this? Keep flying like this, right? You want to flare and touch down. So, understand that this is not a stability problem. CG limit is a control problem. Okay? We are fighting the inherent stability. This is one of the examples where we don't want stability. Didn't get it?
Should the static margin be divided by a C, not alpha?
Oh, yeah, sure. Thanks for pointing that out. I mean, I am allowed to make mistakes. You are not. Yeah. Is this clear? So, we will look at one of the effects one by one. So, what was the first effect that we noticed? Wait. Oh, yeah, okay. So, first effect is that alpha max should be maximum. second CG moves forward, and because CG moves forward, we have a higher static margin, which means that the aircraft is more stable, which means that if you try to keep it at max, if you try to increase the angle of attack, the aircraft is going to try its best to come down to a lower angle of attack. Okay. So, now that is a problem for the pilot, because I want to fly slowly, and for that I need maximum angle of attack. So, and the cherry on the top is, look what happens when you are landing. You need landing gears, right. Now, this is what the landing gear is going to look like, right. Now, we told you that lift and drag, we usually ignore drag, right, but what do you do when something is not generating any lift? It is only generating drag, right. I mean, this is not a lift generating object, it will not be generating very good lift, but it will be generating significant drag, especially if you have something like, anyone has ever seen an Antonov? You have seen 18 wheels, big, yeah, the big aircraft. So, it has like, because of its large wheelbase, its stem is very short to reduce drag, otherwise it would be. So, now the problem is that the CG is usually ahead, right, the CG is going to keep moving ahead in anyways, and now drag is happening this way. What do you think is the moment that this drag is causing on the aircraft? Pitch down. So, look at this, I need alpha max, my decrease in fuel led to increase in static margin, which made my aircraft stable, and on top of that I need landing gears to land. This is not an option. I mean, people have done it, but they did not enjoy it. So, now this is causing extra problems, and the only thing that you can do to combat this is elevator deflection. There is nothing else on the aircraft. I should draw a better, actually that is why I left it here. So, now you see the landing gears causing problem, right. To gain maximum lift, I need to keep my alpha max, and then loss of fuel has already made my static margin higher. So, now my aircraft is extra stable. So, all these things are going like against each other, and I as a pilot do not want that. So, I need to control it now, and the only thing I can do is I can deflect this up, so that if I deflect this up, it creates a force downward, and now I can flare the aircraft and land. So, now you realize that the entire design and sizing of the elevator is kept in mind. Landing is the most crucial phase while designing an elevator, okay? And I hope you get why now. Okay. Moving on, obviously, so this finishes up everything about pitching, right? And then the next, obviously, we move on to lateral or directional stability. So, lateral or directional stability, for that let us have a few conventions first. So, I would come back to this figure here. Do I have? Yeah, I have time. So, I will erase this for a moment, okay, because. So, now let us say that, how should I show it? Actually, it is better to draw it on another. So, if you have an aircraft like this, which is having some velocity v and some velocity u, and it has some velocity w going down, right. So, if I were to draw it in 3D, it would look something like this is u, this is v, and this is w, and then like this would be the total vector, total velocity. Basically, the magnitude of v squared is equals to u squared plus small v squared plus dub squared, right? And it is here that we define angles of attack. Okay. So, if this is the fuselage reference line, right, then this is the angle of attack and this is the side slip beta. So, this is your positive x axis, positive y axis, positive z axis, positive u velocity, positive small v velocity, positive dub velocity. Now, I do not have a marker which represents this accurately, but have faith that the magnitude of this squared is equals to the sum of these magnitudes squared. Okay. Now, this is the fuselage reference line, right. So, the angle that u makes with v is going to be the angle of attack. It is not necessarily in the longitudinal plane. It might be very close because the slight slip velocities are very small as compared to forward velocities, but it can be different. And then this angle is side slip, the angle between v and the complete velocity. Okay. So, now tell me what happens. Let us say that, so this is the aircraft, we are looking at it from the top, and I will draw two more things. So, these are your engine nacelles under the wings, okay. And suddenly the velocity starts coming in from this direction. So, you have a side slip, right, like this is the side slip angle, okay. So, now tell me what is going to happen. Let us look at it very closely, right. Again, these are not going to generate very good lifts, okay. These are just going to act as drag objects. Like you will see some forces which is primarily along the direction of the flow, right, not perpendicular to the direction of the flow. The fuselage, I am not asking you to look at the wings, just the fuselage and the nacelles, okay. They are also a big part of the aircraft. So, what is going to happen? The air is going to hit this way, right, and let us say the CG is somewhere here, and now the air is hitting like this, right. Now, the air which passes through the wing and the nacelle, it will obviously slow down in energy because it has already struck an obstacle. So, now here you have much more diffused air, like you have with high velocity, but it is not as strong, right, which means that the force distribution on this part which was forward of the wing will sum total to a larger force as compared to the force distribution here. Okay. And what does this mean? That if this is the CG, the aircraft has the tendency to move away, which means that your side slip angle is going to increase, and that is why fuselage and nacelles are said to have a destabilizing effect on yawing moment. Okay. Is this clear? So, now what do we want? We desire Cn beta greater than 0. Why? Because as I told you that this is the positive direction, right. This is positive beta and I want to reduce beta. So, obviously, I want yawing moment to go this way. So, Cn beta times positive beta should give me a positive yawing moment, and that is why Cn beta should be positive. Okay. And what is the only thing that's going to help you recover here? Is it only thing or are there multiple things? So, this is something different from pitching. Okay? In pitching you must have seen we only talked about elevators and wings. So, pitching is much
I was saying rudder, but
yeah, rudder is right, but this is one of the most important differences between like pitching and like lateral or directional stability is that yawing moment and rolling moment or yawing and rolling have coupled modes. You will see this later on. These rolling and yawing are coupled to a great extent. Pitching is very much isolated from the two. Okay? Why? What does it mean in simpler words? That when yawing is happen, some rolling is bound to happen, and when rolling is happened, some yawing is bound to happen, but that does not go along with pitch. Why? Because you see, when air comes in this way, right, obviously this air is going to be again slower, so it is going to produce lower lift. This air is faster, is going to produce higher lift. So, the aircraft has a tendency to roll up, although this tendency is small, but this problem arises because of yaw, right. So, even though your main principal control is going to be the rudder, it does not mean that there are no other contributions you need to worry about. Okay. You might have to worry about like asymmetric, for example, how many of you watched Sully? Anybody watched Sully? Come on, it's a nice movie, Tom Hanks. Oh yeah, Hudson. So, it's a good takeaway that as a good pilot, as a good engineer, as a good person who is in tech, okay, if you know your stuff, never expect the journalists or the media to truly comprehend the gravity of the situation. Okay. So, go ahead and watch that movie. It's a very interesting movie. I think every aerospace engineer should watch it. There was double engine failure on flight 159, okay, and he navigated the entire glide path using rudders to finally tip it over from Lower Manhattan to Hudson. So, rudder is your most primary control, but that does not mean that engines do not make contributions. So, if you provide asymmetric thrust, there is one of the aircrafts which made I do not remember, but you can go and look up, which made an emergency landing because its rudder broke up. Its vertical stabilizer, rudder or the vertical stabilizer broke up mid-flight because of wake turbulence, and they controlled the entire yaw using thrust asymmetry. The entire time the pilots were doing increasing and decreasing thrust on the engines to yaw the aircraft. So, there are multiple ways here, like this is not like pitching moment problems. Like if you are like in Boeing, if your MCAS is gone, then you will crash. Here you have options. If you lose the rudder, you can still do it using the engines. If you lose the engines, you can still control the aircraft using rudder. Okay. What else? After this comes roll. So, again, so roll I should do roll again. Right. So, now anybody wants to take a guess that why did I draw these two separate boxes? So, these ones are flaps and these ones are ailerons. Okay. Why? Why are ailerons not put here and like
Farther away, so there's a greater
momentum? Excellent. So, now what happens in rolling? You deflect the ailerons asymmetrically, right? Like if you did it with until now, both the elevators would go down together or go up together. If you take the elevators like one up, one down, I do not know what is going to happen, but it is going to be interesting. And then you have the vertical stabilizer. Okay. That is one control surface, but here ailerons move asymmetrically. So, I still get confused with the positive negative notation, so I will still check. Rolling moment delta A plus positive right aileron up. So, if I push the right aileron up, it is called positive deflection, which means the lift on it is negative, lower or reduced, not negative, reduced. Okay, like I wouldn't say like here positive delta I, which means that you are going to decrease lift. So here, like let's say this is the lift on the right wing, and you deflect this down. So here is the lift on the left wing. Okay, so it won't like be negative. You are right; it would reduce, but then the rest of the wing has much more lift generation. Okay. So, it would, and this would make the aircraft go this way. And why positive delta? Because I told you that xb positive rolling moment. Okay. So, that is why we want this. But now the thing is that again just like pitching, right, do we want like positive, do we want it to like stay like that? If it rolls, what do we want? The aircraft should come back on its own, right? And that is why and that is like there is a natural tendency. Like what is the what helps it come back for the natural tendency? What do we put on the aircraft to make this happen? Heard of the term dihedral? Okay. So, you come, you make an aircraft like this, and then one is a high wing configuration and one is a low wing configuration. Okay. Now, this is structurally a little bit costly, this is structurally a little bit cheap, but here lower dihedral will do the job, here we need higher dihedral. Why? So, you see what is happening with dihedral when, like let's say you are rolling this way, right. So, what is happening? What is happening here locally? Actually, I should draw it even more slanted. Okay. So, if I am rolling this way, I want my aircraft to come back this way, right. So, now what is happening? The air flows like this above the aircraft, and here the air flows above like this. So, now I want my lift to increase on this side, right. If I am rolling this way, to come back, I would want the, after I switch off my ailerons, obviously like it will come back after I switch off my ailerons. After I switch off my ailerons, the air is going still flowing this way. So, we would need a higher angle of attack, local higher angle of attack here, and we would need a lower angle of attack here. So, that it has a natural tendency to come back. And the same thing goes on for like sweep, that is the same reason why we have sweep and so on and so forth. I think that is all as compared to, and obviously if anyone has any doubts regarding these two relations, then just let me know right now. I am not going to rederive them, I am going to do an example based on one of them. So, Cn beta is given as negative eta V, which is again efficiency of the vertical stabilizer, horizontal vertical stabilizer volume ratio times Cl alpha V times tau rudder. Same thing as your elevator, the same concepts hold here, right. And then using same concepts, we write the deflection for rudder, but because aileron is big, we need to really integrate its area, and we would have 2 CL alpha of the wing tau a, again the same concept, ratio of the aileron to the wing surface, SB integral y1 to y2 cy dy, where y1 and y2 are what? So, if I were travelling along this y starting from 0, this would be y1 and this would be y2. Okay. Now, let us do one example. Let me see if I can switch it on now. No. Sorry.
Oh, it's okay.
Okay. Now, how much time do I have left? 5 minutes. Excellent. Now, wake vortex encounter, this is like I was talking about this earlier as well. So, let us say a huge aircraft is leaving the airport. So, what is going to happen? It is going to produce this wingtip vortices, right, which are going to be coming out of its wingtip. And if it is moving this way, then here the vortices will be curling like that, and on the other side the vortices will be curling this way. So, now I will make a sketch from like the behind of the aircraft, and we have been told that one of the aircrafts is running into this. So, if you look from behind, this is how it looks like. Okay. And there are 3 crucial positions. What is going to happen here?
Cancel out.
They cancel out, but
There's a downwash.
there is a huge downwash. So, you as a pilot are wondering that I am flying at 110 knots, this is the cruise speed, why am I not getting lift? Why is my aircraft not taking off? Because the actual angle of attack is very low, right. So, here you will not be able to take off at all. Okay. What is going to happen here? So, this is the smaller aircraft, right, if I look at it from the back, and this is what is happening, right, which means that, so already the air was coming like this from the front, and now you have these components of like right, which are going to induce a roll moment. And if you do not use the ailerons, what is going to happen? You are ultimately going to roll, right. The same thing, but the other way around. And what happens if I were coming like this? You would pitch down. Okay. In either cases, you will have a tendency to pitch down, a huge tendency to pitch down. Okay. Also, there will be a loss of lift because your wings will again encounter a downwash. Okay. So, there is I will send you the notes for today, but the crucial condition is that my capability to, so this is the rolling moment due to the larger aircraft, this should be less than or equals to dynamic pressure head times S times B times CL delta A times delta A max for my follower aircraft. So, F denotes the large aircraft and G denotes the follower aircraft. So, this is rolling moment induced due to the large aircraft, and this is the rolling moment that I can generate with my ailerons on the small aircraft. And if this is not able to combat this, then I won't be able to come out of the roll crash. So, you will see that some values have been provided, and yep. You should also remember this, that the circulation or the strength of this vortex is dependent upon, okay, sorry, I made a mistake. So, this should be F, this should be G. So, this is follower, this is the large aircraft. Right. So, this strength of this vortex is directly proportional to the weight and inversely proportional to the velocity of the larger aircraft. So, when is this combination at its worst? While takeoff. Why? Because the large aircraft has full fuel on. So, the weight is very high, and because it is taking off right now, the velocity is low. So, which means you are dividing by a small number and multiplying by a huge number, which means that gamma is going to be big. So, if you try to take off with a Cessna after a Boeing 737 or Boeing 747 has just taken off the tarmac, best of luck. You won't get into the air.
What is gamma in this case?
Gamma is the strength of the vortex. So, this vortex is mathematically defined as follows. Let me point it out. So, in this center of the vortex, okay, like within the, so let us say this was the large aircraft and this was the wingspan B, right. So, in this region of the vortex, this is like basically how do you find out, so this is moving like this, but then how do you find out the exact velocity contribution, right. You say that velocity contribution is, so if I am given that gamma is my velocity contribution, gamma is my circulation strength, then I can get the velocity as, sorry, and then I can get the velocity as this times the radius times some constant. So, inside the vortex, the velocity linearly increases with radius, right. That is why you have like higher velocities here. So, there is a higher tendency to for the tips to roll over. So, now you are going to go down. I have provided some hints how you should approach the problem, but first of all, what are you going to do? You are going to take the parameters of the large aircraft and find out the strength of the vortex. Once you know the strength of the vortex, now you know the velocity distribution. Once you know the velocity distribution, you are going to integrate it and get the induced rolling moment by the large aircraft's vortex on the small aircraft. Okay? And then you are going to go and compute that if I put my ailerons at maximum deflection, plus or minus, does not matter. Like if you are here, then you would want a positive deflection, sorry, a negative deflection. If you were here, you would want a positive deflection, does not matter. Okay? What matters is the magnitude. So, if the magnitude of this wake vortex, the rolling moment due to the wake vortex comes out to be greater than what you can produce on your own aircraft, then that is not a safe operating condition. Okay?